In this video, I want to take a look at the method of undetermined coefficients and use it to solve a non-homogeneous fourth order differential equation. Now, the method here is very similar to what we did with second order equations, but there's just a couple of things that could go a little bit differently, but generally it's pretty much the same. So here we go. Here's my differential equation. I got the fourth derivative of y minus 4 times the second derivative of y is equal to t squared plus e to the t. Now, similar to second order, if you're going to get the general solution of this non-homogeneous equation, what you need to do is first find the general solution for the homogeneous equation, and then find one particular solution for the non-homogeneous. So the first thing to do is to solve the homogeneous equation. So stick a 0 over here on the right hand side instead of whatever else was there. Now to do this, because we have constant coefficients, we're assuming that y equals e to the rt and plugging it in and ending up with this polynomial equation, r to the fourth minus 4r squared equals 0. Factoring that, you can factor out an r squared, and then the r squared minus 4 is r plus 2 and r minus 2. So what I have is I have four solutions, r equals 0, r equals 0, r equals minus 2, and r equals 2. Because of that repeated root, I have to multiply by t, right? So the r equals 0, we saw this in a previous video, corresponds to a constant, because that would be e to the 0t. Which is just 1. So C1 times 1 is just a constant, being a solution to that differential equation. Likewise, because 0 is a root twice, t times e to the 0 is just t, and so a constant times t is also a solution. Actually, this makes sense when you think about it, just like we did with that constant in a previous video. C2 times t, the first derivative would be c2, the second derivative would be 0, the third derivative would be 0, the fourth derivative would be 0. And when you look at this equation, it doesn't involve the first or second, the function or the first derivative. It only involves the second derivative and higher, and those are all 0. So sure, 0 minus 4 times 0 is 0, and t is a solution. Okay. Now, the negative 2 means e to the negative 2t is a solution, and the 2 here means that e to the 2t is a solution. And that shouldn't be c raised to the 4, that should be c sub 4. Yeah, that's better. So now, I have the general for the homogeneous, I need to find one particular solution for the non-homogeneous equation, the original equation we started with. Now I'm going to do this in two parts, as I explained in the previous video. Because the right-hand side here is a sum of two things, I'm going to handle the t squared first, and then I'm going to come back and handle the e to the t. You could do it all at the same time. It really isn't that much more work in this case, but in some cases when each of these takes a fair amount of work, it's just easier to keep track of when you can separate the two. So I'm going to choose to write it as the left-hand side equals t squared, and then that same left-hand side equals e to the t. So I'm going to take each of these as g1 and that one as g2, right, and solve each of these individually. So for this first equation, it is a second-degree polynomial over here. So I'm going to guess for my particular solution a second-degree polynomial. The arbitrary second-degree polynomial would look like at squared plus bt plus c. However, there's a problem here because c and bt are already solutions to the homogeneous equation, right? That a constant and a constant times t are part of the homogeneous solution. So there isn't any way they're going to be part of the particular solution. So what I have to do then is I have to multiply by a power of t until none of this stuff looks like it's part of the homogeneous. So if I just multiplied by t, this would be a t cubed, that would be a t squared, this would be a c times t, but c times t is still part of the homogeneous solution. So I got to multiply by t squared. It's actually possible on a fourth degree polynomial that you would have a root in there 4 times. So it's possible that that you could have had here C1, C2t, C3t squared, C4t cubed, in which case in this one I would have to get up to not having even t cubes in there. So I'd have to go to a t to the fourth power that was multiplied out here. Okay, but in this case, because it's only r equals 0 is a root twice to the homogeneous, to the characteristic equation up there, then I have to multiply this by t squared to get that out of there. Yeah, it's still, though, a quadratic here that I start with, and then I multiply by t squared. It's not like I'm writing down an arbitrary fourth degree polynomial, because a fourth degree polynomial would have not only a fourth degree, a third degree, and a squared term, but it would also have a linear term and a constant term. So there'd be 5 variables there, but I don't need all 5. Because this is a quadratic, I need the general quadratic, but then I just need to multiply by a t enough times so that none of this stuff becomes part of the homogeneous solution. Okay. So anyway, here's what I have. I've got this fourth degree polynomial, taking its derivative, its second derivative, its third derivative, its fourth derivative, right? And then plug it all in. Actually, I really only need the fourth derivative and the second derivative. So plugging in the fourth derivative minus 4 times the second derivative, I need that to equal t squared, right? If it's going to be a solution to that equation, that's what I need to have true. Rearranging some things here, so the t squared is a minus 48a t squared. There's a negative 24bt there, and that's it for the t's, and then there's a constant of 24a, and there's a constant of minus 8c right here. If this polynomial on the left-hand side is equal to the polynomial on the right-hand side, then all the corresponding coefficients have to be the same. So I need that the coefficient in front of the t squared here equals the t squared there. So negative 48a has to equal 1. Likewise, that would solve to be, these arrows didn't really work out very well. Anyway, a would be negative 1 over 48. The linear coefficient here is negative 24b, but the linear coefficient over here is 0, so that would tell me b equals 0, and then the constant coefficient on the right-hand side, 24a minus 8c, has got to equal the constant coefficient of 0 over there on, well, that's the left-hand side, and this is the right-hand side. So there's this. That would mean that c equals 24a over 8, but a was already determined as that. Plug in the negative that, and you get that c is equal to negative 1 over 16. So the part of the particular solution that's going to give us the t squared over here is this. Because we said it was, what was it? Where were we? A t to the fourth plus bt cubed plus ct squared. So I've got the a t to the fourth plus 0t cubed minus 1/16 t squared. Now, we want to find the other part of the particular solution. That is, we want to find the part where the left-hand side of that differential equation equals the e to the t. Okay. Now, one thing I noticed, I have to be careful of, so I'm double checking, is that e to the t was not part of the homogeneous solution. Coming all the way back up here, right, the homogeneous had a couple of exponential pieces, but it wasn't an e to the t. It was an e to the negative 2t and e to the positive 2t, but not e to the t. So I'm okay then in guessing for yp, which I'm just calling y2 here, because it's an e to the t and it's not part of the general solution to the homogeneous, I can just say I'm expecting a times e to the t. Okay? And this is a remarkable function because its derivative is equal to itself, so is the second derivative, the third, and the fourth. They're all equal to a e to the t. So when I plug them in to the differential equation, this one right here now, there's the fourth derivative minus 4 times the second derivative. That's supposed to be e to the t. So I've got negative 3a e to the t equals e to the t, which means that negative 3a better be equal to 1, and a would be negative 1/3. So the particular solution for this differential equation is negative 1/3 e to the t, which makes the particular solution for the original differential equation the sum of the two of them. So this was the part we got to get the t squared, and this is the part we got to get the e to the t, which now makes the general solution for the original equation here. There's the first four terms here are the general solution for the homogeneous equation, and then we have the particular solution to this non-homogeneous equation. Okay, so very similar to what you did in second order equations. It's just there's more going on and a few more things to be paying attention to. So we'll do another example in the next video.